Frequency domain sampling and reconstruction of signals. Here we are going to consider a continuous spectra. That means spectral domain is a continuous one. We are going to make some of the samples. From those samples, that means spectrum is going to be discretized. That we want to use for the reconstruction of a original signal. So if it is useful to reconstruct the original signal from a discrete spectrum to the signal, then we can use a discrete spectrum only instead of having continuous spectrum, because as we know, continuous spectrum will take more bandwidth as compared to discrete one. So that we are interested in discrete spectrum. From that discrete spectrum we want to reconstruct the original signals. Let us consider x of omega. X of omega is nothing but continuous spectrum. This line will indicate you continuous spectrum. This continuous spectrum, from this continuous spectrum, we are interested to make some of the samples. That samples are going to be collected at k del of omega interval. K del of omega interval, we are going to collect some of the samples. But once the samples are completed, discrete spectrum will have a bandwidth of minus pi to pi or 0 to 2 pi, minus pi to pi or 0 to 2 pi. So that each and every sample was indexed by k. If k equal to 0, first sample, k equal to 1, next one, k equal to 2, next sample, up to so on. If you collect n samples, that means 0 to n minus 1 samples are going to be collected. Then each and every sample will be indexed by kth representation. So that is nothing but x of k del of omega. X of k del of omega. But here we are interested total spectrum to be divided into n samples. So that total spectrum equal to 0 to 2 pi. The bandwidth equal to 2 pi going to be divided into n samples. So instead of representing that del of omega, we are going to make that exact del of omega equal to 2 pi by n into k. We will see that representation. So x of omega replaced by 2 pi by n. Total spectrum divided into n samples, each sample indexed by k. So that x of omega formula equals summation n equals 0 to n minus 1. This periodic signal e power minus j omega. That means 2 pi by n into k and e power minus j omega. So in case of Fourier transform form samples, that was indicated by summation L equal to minus infinite to infinite x of n minus ln, where L can vary from minus infinite to infinite. Then this thing is going to be notated as xp of n, periodic signal, splitted into these many summations. L equal to minus infinite to infinite x of n minus ln. This one will be equivalent to representation of periodic signal. So we are going to replace this expression by periodic signal xp of n 2 pi by n into k equal to summation n equal to 0 to n minus 1 xp of n e power minus j 2 pi by n kn. Fourier series of a discrete periodic signal going to be given as xp of n equal to summation k equal to 0 to n minus 1 ck e power j 2 pi kn by n. We know this expression. N equal to 0, 1 up to so on n minus 1. Then coefficients, Fourier coefficients, ck equal to 1 by n summation n equal to 0 to n minus 1 xp of n e power minus j 2 pi kn by n. K equal to 0, 1 up to so on n minus 1. Then we know that already just derived expression x of 2 pi by n k equal to summation n equal to 0 to n minus 1 xp of n e power minus j 2 pi by n kn. In place of then by comparing this expression with this above expression, we can write it as ck equal to, compare these two. So this expression going to be compared. So summation n equal to 0 to n minus 1 xp of n e power minus j 2 pi kn by n is the CK formula. CK formula. In this case, you are going to substitute x of 2 pi by n into k. We are going to substitute here. So CK equal to 1 by n x of 2 pi by n into k. K equal to 0, 1 up to so on n minus 1. So we establish a certain relation between Fourier series coefficients and discrete spectral representation. Ck is the Fourier series coefficients and 1 by n x of 2 pi by n into k is the discrete spectrum. We establish some relation here. Then xp of n. Here we are going to substitute xp of n equal to summation n equal to 0, k equal to 0 to n minus 1 ck e power j 2 pi kn by n. In place of ck, in terms of discrete spectrum we are substituting. So that ck is going to be replaced by 1 by n x of 2 pi by n k. So xp of n equal to 1 by n summation k equal to 0 to n minus 1 x of 2 pi by n k e power j 2 pi kn by n, where n equal to 0, 1 up to so on n minus 1. Then x of n equal to xp of n. X of n equal to xp of n. For the interval 0 to n minus 1. For the interval 0 to n minus 1, the periodic signal going to be truncated and it will appear as a x of n. It will appear as a x of n. So that x of n equal to xp of n over the interval 0 to n minus 1 and 0 for the elsewhere. So xp of n is existing over this interval as a x of n. So that x of n equal to 1 by n summation k equal to 0 to n minus 1 x of 2 pi by n k e power j 2 pi kn by n, because the periodic signal we truncated into some sequence. We truncated into, because periodic signal is nothing but a sequence. xp of n is a sequence repeating. So that we are going to reconstruct the one set of sequence only, x of n. In place of xp of n, we replaced that x of n. See this, x of n, this is a periodic signal where L is the length of the sequence. If L is smaller than capital N, then this will be reconstructed very simply. If L is greater than, in this case L is greater than, first case is nothing but this is the original sequence. For first case n is greater than or equal to L, no aliasing. So we can truncate this, we will get. But in case of n is less than as compared to L, that means we are reconstructing only n samples, means n is less than L, aliasing effect existing. From this spectral domain to time domain, if number of samples we are reconstructing, capital N is less than capital L, then aliasing, we are going to lose some of the information. If n is greater than L, we are able to reconstruct the original signal with a proper manner. Here this is appearing. This is the length of the original sequence, whatever you are expecting. Then capital N should be greater than. If n is less than, aliasing going to be existing. Then x of omega equal to summation n equal to 0 to n minus 1 x of n e power minus j omega n. In place of omega we replaced that it is 2 pi by n into k. 2 pi by n into k. This is x of omega. X of omega equal to summation n equal to 0 to n minus 1 in place of x of n. Just now we derived this, x of n equal to 1 by n, k equal to 0 to n minus 1 going to be replaced. These summations are going to be interchanged. Summation k equal to 0 to n minus 1 taking outside, x of 2 pi by n k, and the remaining term going to be written like this. This e power going to be combined here, minus j e power minus j omega minus 2 pi k by n into n. This expression, this is, are you clear this? So here x of 2 pi by n into k, this is a discrete spectrum varying from 0 to n minus 1. From this spectrum interpolated with a function e power minus j omega minus 2 pi k by n into n, then we are able to reconstruct the original spectrum. this is the interpolation function. This is the interpolation function. That interpolation function actually e power minus j omega is going to be shifted by 2 pi by n into k shifts. This is going to be shifted version. We have to shift those many shifts. So this is the function x of omega equal to x of omega for n equal to 5. We got this. Simply x of n, see this x of n is original signal. For this x of omega is nothing but original spectrum, continuous spectrum. We got this. Suppose x of n having less number of samples. That means in this case, if you are collecting less number of samples, then this spectrum according to the given expression will going to be less. N equal to 5 considered, 5 spectral samples going to be collected. N is going to be increased more, then spectral domain also going to have more number of spectrums. But you can observe this, the sample whatever we are going to collect in spectral domain doesn't alter the shape of the spectrum. In the previous case, whatever the spectrum shape we have, the same shape going to be continued here also. So DFT, discrete Fourier transform. From this previous derivation, x of 2 pi by n into k equal to summation n equal to 0 to n minus 1 xp of n e power minus j 2 pi by n kn. Then x of k, instead of writing everything 2 pi by n, already we know that 2 pi radians going to be sampled into n. X of k equal to summation n equal to 0 to n minus 1 x of n e power minus j 2 pi by n kn. X of n inverse transformation equal to 1 by n summation k equal to 0 to n minus 1 x of 2 pi by n k e power j 2 pi kn by n. Inverse transformation. From the previous derivation, we obtained that x of k equal to summation n equal to 0 to n minus 1 x of n e power minus j 2 pi by n kn. Then x of k equal to the same formula we rewritten, discrete Fourier transform. Then x of n equal to inverse discrete Fourier transform. Then we will wind up this session.